I just wait for you to.
Yeah.
But let's first see Julieta.
Good morning. Very happy to start the morning session. We have now today industry lookout, and especially to introduce Dr. Julieta Ross. She's a doctor in computer and electrical engineering, and she has her own startup company. And maybe most of all, she's a good friend of mine. So please, convergence of nature, data, and artificial general intelligence.
Yeah, and she only said the good things because we're friends. She didn't say anything bad. But anyway, I'm very happy to be here. I gotta tell you, when Ludmila asked me if I would present, I was very, very shy and uncomfortable because of the nature of the conference, right? Pure mathematics, and you can do things that obviously some things that I can't do. So it's been a true enlightening week for me, and super excited to have met most of you. So anyways, I want to share with you today, we only have an hour or so I want to share with you today sort of the other side of all the foundational work that you're doing, how we're actually taking all this foundational work and applying it in the industry. I always say, it sounds negative, but it's not. I always say that my job and the people in my space, we actually weaponize AI, not in a bad weapon organization, right? But from the perspective that we take all of the incredible work that is being done by organizations like pure mathematics or applied mathematics, and we are able to implement this in ways that you may not even think about. So I just want to give you a flavor of the things that we are doing, and hopefully the idea is that hopefully this conversation will sort of trigger in you sort of the perspective of things that we need to be thinking about and looking into doing in the future. Okay, so as Nina mentioned, I have a PhD in electrical and computer engineering here from the University of Miami from over 20 years ago. My dissertation, my master thesis and my dissertation was in AI. And this is back 25 years ago when we didn't have PyTorch or the frameworks that we use today. Doing AI back then was very, very difficult. We spent most of our time coding, right? The guardrails that we need to be able to run these models. Most of my work, if I spend 100 hours doing a project coding, 80% of that time, 80 hours, was coding backpropagation, coding all these concepts, forward propagation, backpropagation, all these concepts that today we take for granted because we literally get the libraries from PyTorch and we have 10 lines of code from these libraries and these frameworks, and we can do it pretty quickly. So on the good side, doing that, it gave us, some of us going through that 25 years ago, it gave us the foundation to think about what it means to do this, what's actually going on in the background. So that foundational was tremendous. So that's my background. And I stayed, when I graduated from my PhD, I actually stayed as a professor here at the university, a research professor, for a few years. The university hired me, but then I left. I went to the industry, and I've been in the industry, many verticals, many corporations, very large global corporations, working for the last 25 years. So I'll share some of that as well. So today we're going to talk about the convergence of nature, data, and AI. So kind of thinking beyond the algorithms that we develop and the models that we code from those algorithms, but truly thinking about what is intelligence, beyond the way that we think about it today, which is the notion of neurons, right, and the brain. We have intelligence in many other areas that we're not even thinking about when it comes to AI. And then we're going to briefly start talking about artificial general intelligence. Okay, so those are the topics we're going to try to cover today, from neurons and mathematical neural networks to non-nervous systems intelligence. We do have intelligence, we have projects that we're working on. We do have intelligence in systems or entities, we'll talk about some examples, that don't have a nervous system. So how do we think about modeling that? How do we go about modeling that? We're going to talk about data. 75 to 80% of what we do when we build AI systems, it's data management, capturing the data, organizing that data, cleansing the data, making sure the data is not biased. And all this data work consumes AI practitioners most of the time of what we do. So, and something else to think about when it comes to data is that the mindset that we have today when it comes to these models and algorithms is that we take data, we build our models, we take this data, we train the models with this data, and then we train them and then we run the models in production, right? By the time we take this, if we have a whole spectrum of data and we take a subset of data to feed and train our models, that notion of taking a segment of this data is already introducing bias in the data. Because how do you choose what to take? How do you choose what not to take? Do you even have access to all this data? I mean, what data do you have access to? I can tell you, I spent many, many years working with the Everglades Foundation, in the Everglades National Park and other areas, trying to figure out, what are the invasive species that we have, what panther population, and just environmental projects. And you have to go and collect data, but the data that you collect is segmented based on the area where you're located. So by default, it's already biased. So there are other ways that we're exploring on obtaining and getting data, and it maps directly to all the conversations we've had in the last week on how do you tokenize this data and how do you manage this data. And then we're going to talk about a potential path to AGI, artificial general intelligence. We haven't covered AGI this week. AGI is a conversation that we can, it could be like a whole week just to talk about AGI. So we're going to start talking about that. So the first thing we need to really understand is this notion of intelligence. The struggle to understand intelligence goes back over 2,000 years. So there's a great book. I mentioned a few books as I go through this, and you can always write me if you want to learn, more about the things that the books that we wrote or the books that we're working with or some of the books that we've read. But there's a great book called In Our Own Image that talks about all of these different, throughout time, 2,000 plus years, all these different interpretations of what intelligence is to us, to humans, and how do we envision intelligence. And you'd be surprised about, some of these definitions. So the original, most going back in time, the first mentions of intelligence goes back to, obviously, our religious books, whatever book, religion, if you practice religion, if you read any of the religious books, the earliest metaphors, humans were formed from dirt or clay or however, that God, the concept of a God, created you. And this God, an intelligent being, infused intelligence in your spirit into you, into the mold of you. So these are the original metaphors of intelligence. It came from a God or a spirit that came down to us. Later on, the invention of hydraulic engineering in the 3rd century led to the popularity of hydraulic models of human intelligence. The idea that water or liquids, the flow of different fluids in the body, accounted for both physical and mental functioning. So this notion of hydraulic reinvented this space. It became an area of research. So whenever we go to a new area of research, the notion of intelligence tends to be historically explained by that area of research. So the hydraulic metaphor persisted for more than 1,600 years. For 1,600 years, we thought that intelligence came from fluids in the body. By the 1500s, we invented the notion of springs and gears, and eventually inspiring leading thinkers to believe that humans are complex machines. And the motion of these gears and the motion of these springs is what trigger the notion of intelligence within our bodies. So there are many books in this particular subject, which are fascinating. 100 years later, there was a new perspective of intelligence. The philosophers or thinkers thought that it came from small mechanical motions in the brain. It took another 200 years or so, 100 to another 200 years, when we discovered electricity and chemical functions, chemical formulas. This led to new theories of human intelligence, again metamorphically speaking. So we thought at this point in time, in the 1700s, that intelligence came from the notion of electricity, the notion of chemical reactions in the brain, and which is fascinating and interesting.
It's still true today.
It's true. I was going to say, what's fascinating in industry is that we you'll see the next one or two iterations of these. We went into other future thinking areas of these, but the notion of chemistry is coming back. The notion of electricity kind of stuck around because we translated that to digital machines, Boolean algebra, based on electricity on and off, right? So in the mid 1800s, inspired by recent advances in communications, philosophers started thinking and writing about about intelligence, the brain and intelligence mimicking machines like the telegraph. They were convinced that this was the way that we think. And then the latest, of course, there's a bunch of subsets in between, but the latest and most recent state that we're in is by John von Neumann, right? So in 1958, John von Neumann stated that the function of the human nervous system is primarily digital. And this just happened 60 years ago. This happened 60 years ago. Remember that some of these phases that we went through took 1,600 years. So 60 years ago, we started thinking that the brain could be mapped as a digital machine. Although he acknowledged that little was actually known about the role of the brain and what role it played in human reasoning and memory, he drew parallel after parallel between the components of the brain and computing machines, which is fascinating. This is where we are right now. So it's only been 60 years, and I think it's pretty safe to assume we should not be surprised if this eventually evolves into something more complicated beyond the fact that we believe that the human brain is only digital, which is everything we do today. So what's fascinating about the state that we're in right now is that it just basically happened 60 years ago. If you see the exponential evolution of inventions, everything that's happened since the von Neumann machine was created. Remember that this is in 1959, 1960. In the 1930s, 1939, actually almost 1940s, 20 years before, is when Shannon, who was doing his master thesis at MIT, he was working with his master thesis advisor who had created a mechanical machine to try to simulate intelligence with a mechanical machine based on previous knowledge. And he asked Shannon in the 1939, 1940, he asked Shannon to start thinking about ways to explain how intelligence and automation could happen, the formulaic formulas for this mechanical machine. And then Shannon, who was doing his master thesis at the time, remembered that when he was doing his undergrad work a few years before, he read a paper in a class that he took in the philosophy department at his undergrad university, where he was reading the work that Boole did on Boolean algebra, and he said, "Oh, that's logical on and off. His mechanical machine is powered by electricity on and off. I can map Boolean algebra to these." So he married both together, just because the guy was doing his master thesis. He remembered a paper that was written 100 years ago. He married the two together and 20 years later, fed into the notion that von Neumann created his machine, his digital computing architecture, and the brain was mapped to biological processes. on and off to binary, and then from Shannon to von Neumann to now, it's a matter of 50, 60, 70 years. Everything that we talked about this week, every aspect of what we do in technology and computing just happened. I mean, literally just happened 60 years ago, which is incredibly fascinating. So that's actually, I think it's incredibly fascinating, right? So, but the truth is that we still cannot define intelligence. Like if I ask any of you, do you actually have a good definition of what intelligence is? Maybe I'm wrong, but I don't think you know, right? Here during the week, we actually heard some pretty amazing, we had pretty amazing discussions on the notion of meaning. How do you use a transformer to go from one set of data encoded to another set of data? Oh, I think you were talking about that. And how do we, from one set of data to another set of data, how do we keep the meaning of both sides the same, right? So we know that meaning, we kind of were thinking about the notion of meaning. We also talked about the notion of, the notion of the difference between learning and knowledge. But as a computer engineer, can I code it? Can I code that? I don't know how to code that. How do we develop that? So we still don't have a common understanding of what intelligence is. Therefore, it's tough to code. We can't develop that in systems. There are no known equations to define and codify reasoning, consciousness, emotion, laughter, and love in the context of digital machines, von Neumann machines. Having said that, we're going to talk about this in a little bit in a couple of slides. We can't do that in a digital way, because what? We do know from a physiological perspective, from a medical perspective, from a chemistry perspective, we have a better understanding of what happiness is, for example. We know that happiness in the body, when you feel happy, your levels of serotonin, neurotransmitters are a certain way, your levels of GABA and other neurotransmitters are a different way. So there are other ways to code some of these things that are not necessarily the way that we're thinking about coding today. Okay? So which is fascinating. Programming of computers has become more sophisticated in the last few years, but if our goal is to build machines that can objectively reason, anticipate future events, have emotions, imagine possibilities beyond what we train them to learn, we're still very far away from getting there. In the way that we're thinking about today, in the context of this last phase. So the question is, what do we need to do? What's the next iteration of these to help us get there in a better way? So envisioning the brain only as a digital system without taking into consideration biological processes and protocols as the foundation of what intelligence is, has resulted in many blind alleys in artificial intelligence. Yeah.
I had a question about Shannon. So when he was developing information theory, right? It was basically in the discrete setting, relating the entropy to the channel capacity and these things. But my understanding is that analogous definitions in the continuous case are a little bit contentious. There's not, how would you say, the encoding requires sort of infinitely many, infinite entropy description. So is that a basic sort of first order thing to resolve before you would even go?
Absolutely, yeah. It's not. We're going to talk about the architecture of the brain versus the architecture of how we're coding, trying to replicate the brain in the von Neumann machine, right? So we don't, the way that we're approaching this today, with the perspective that we capture data and we train, and only then we can do inference. It's not continuous. By the time you do inference, the data's already old. Does that make sense? We as human beings, we run on molecular programming. Why? We run on carbon computing. We don't run on silicon, obviously, right? So everything that's living, the notion of intelligence, consciousness, and emotions runs on carbon computing. which is molecular programming, right? Which is continuous. Like you said, you're absolutely right. But we are building or trying to figure out how to build these capabilities in semiconductivity on and off, very hard rigid things, right? Does that make sense? So the architecture is so fundamentally different that we can keep working in this space. We will, we're doing amazing things, we're building incredible things, but can we truly get to intelligence? I'm not sure, yeah.
Yeah, so thank you very much. Yes, of course, this is completely different from silicon chips. But I was wondering, you're saying the data is already old when we train and we make inference. If you continuously train, for instance, an RL model, it's old by an amount of time that is very very close to the response time in biological system.
Yeah. You're right, but most of, if you can,
I agree,
you're
it's
absolutely
completely
right.
different. Of course.
No, you're absolutely right. Based on what we've seen, the typical architecture of AI systems that are out there today, they're pre-trained, even all the large language models, right? I mean,
No.
so like if you, I don't know if you know Jimmy Buffett, the guy, the singer, who my husband loves him, Key West, figure Key West, he actually sings Jimmy Buffett. When he died, if you ask ChatGPT if he was still alive, he would say, of course he's alive, he's probably in Key West right now, right? But he was dead, so that's the point. Does that make sense? Yeah, we could eventually go into a state where we could be training while we do inference, but we're not there yet.
I was just thinking because like if you see humans, it seems that when we see something, we keep learning time.
We keep learning, absolutely. So we are, it's a notion of us with a different molecular programming model, we continue to learn during inference, right? So, yeah, any other question? Yeah.
What do you think? I mean, can we define intelligence if actually we don't know if reality is continuous or discrete or analog or digital? Can we move forward in that without knowing that?
I'm sorry, say that again? Can we move forward if we don't know?
If the reality is continuous or discrete, or if it is digital or analog.
So we can move forward. That's the way that we're building things today. I'm going to share some of the projects we're working on. It's really amazing, incredible things. Of course, we can move forward, right? We can do great things, but there's a difference between how the way that we're approaching AI today is helping us automate and augment humans versus truly reaching intelligence. The way that we're going, the way that we're moving today, in my opinion, my honest opinion, my humble opinion, I don't think we'll get there. So I think that we're going to get to the point that we're going to see very, very soon, because these are happening exponentially faster from one to the other. We're going to see very soon a new iteration of this, which is going to be these plus something else. That's going to get us there. And I'll give you some ideas of what we're thinking, okay? But remember that as we do these, we still don't understand these. So we're going to have to, the work that you do, the foundational work that you do, understanding the functions and the equations, trying to figure out the algorithms, that's going to have to happen. We just don't know how to do that yet, okay? Okay, so the point here is that we have to start envisioning the brain more than just a digital system. There are things, if we want to code laughter, fear, consciousness, we can do that chemically. We have a gentleman here who's doing his PhD at the School of Medicine. He can tell you everything about chemistry and how we can encode these with neurotransmitters. But we're not thinking that way. So it's going to be a combination of thoughts in different spaces. So the major challenge, how do we extend our current research in AI beyond silicon chips and digital computing to an architecture that is closer to the architecture of the brain? And that means not semiconductivity, silicon on and off. That means conductivity, carbon computing, and other potential ideas, thoughts, molecular programming, and new ways to capture data. We're going to talk about that too. How do we derive profound mathematical understanding of biological processes and intelligence in this context? This is something that only really people like you can do. You are the brains behind looking at processes, looking at functions. You were saying that you have a brilliant PhD student who can look at data. I can capture all data all day long from my experiments. You have a PhD student, or you had a PhD student, who can look at a set of data and a graph and immediately figure out the formula behind it, which then we can use to build our algorithms and our systems. We need that, right? Can we develop algorithmic approaches to learning, mimicking the functionality of the human brain? And what about animals and plants? So we're going to talk about plants. There's a lot of intelligence going on in plants. We're not even paying attention, but we did a lot of experiments on that. So the road to AGI has 3 super high level, 30,000 foot looking down stages. We are here. We are still talking about narrow intelligence. What does that mean? It's the notion that we look at one-off scenarios. We try to find the data, the formula for that one-off scenario. We solve one problem at a time, and machine learning is heavily used. We're here. We're just at the beginning. Ideally, at some point while I'm still alive in the next, hopefully 50 years, we'll get to the notion of AGI, which is systems that are as smart as humans across the board. And I'm not talking about remembering like every book ever written from the Library of Congress. I'm not talking about LLMs that are fed all this information and then statistically tell you, something, right? I'm talking about systems that now can potentially work with a world model, or for humans, we call them mental models, and understand from my perspective, we can both be looking at the same thing, but with different mental models. I might get something out of this, and it might mean something to me that might be meaning something different to him, right? And this is truly going from machine learning to machine intelligence. So this is something that we're trying to think, how do we go from the traditional von Neumann architecture to something enhanced that can get us there a little bit quicker? And in the future, I think I'll definitely be there. The future is super intelligence. I don't even know if we'll ever get there, but that's, I don't know, Mina, 100 years away, 1,000, I'm not sure. But
Probably much earlier.
you think so?
Yeah, because people are working on enhancement all the time. There's
Okay.
a lot of people that are doing that, and we need, of course, to have new ethics for that, but people are
Absolutely,
working on
yeah.
that.
Okay. Okay, Mina says we'll do a bet. Mina says 100 years. I say 1,000.
So the obvious question is, Terminator. Okay. The Matrix. I guess. I'm trying to figure out how to phrase this question. How do we know that it can even be achieved? AGI, alone ASI. Because I feel like there's like a real bedrock thing in this field about consciousness itself, and I had this discussion with this guy recently about that, and sort of gave him a thought experiment, like, okay, if I take a bunch of carbon atoms or sulfur or these other things, and I just kind of build a brain out of it, right? Where is the consciousness, right? Because the constituent matter is atoms.
Right.
And like as humans, I guess we make a distinction between like I'm conscious and the chair is not, or
That's
whatever, right? So
you are asking all amazing questions, right? So there are so many things there in what you just said. We still don't know what consciousness is, right? I know that I'm conscious. I know the chair is not, right?
So how do we?
Right.
Sorry, not to interrupt, but
Yeah,
then
yeah.
how do we know it's sort of not just a mimicry machine, right?
Right.
So, like how do we know it's not just a mimicry device and it's
That is mimicking, like it's
Yeah.
repeating statistical feedback. Yeah.
mimicking consciousness is what I mean. Yeah.
And exactly the continuous of the question, which is, do you think we can achieve this kind of, let's say, consciousness, let's say, in 100,000 years, without biological computing, or even
No.
without recreating something that is close to life?
I think not even forget that. I'm talking about here for now, right? I think that for us to go to anything closer to here, we are going to have to involve other things beyond digital computing. And I'm not talking about growing a brain in a deep fish. I'm not saying that. What I'm saying is, if I want to understand how you're feeling right now, say that right now, if I'm talking about AI, really what I'm translating that to is I need to be able to code it. How the heck do I code it? I can't. But if I, as a human being, a molecular programming program human being on quantum computing, I can look at you and I can tell that you are a little bit interested, at least because of your posture, because you're leaning forward, the questions that you're asking. There are things that I'm gathering by looking at you, the data points, biomarkers that I see, the data points that I'm gathering are telling me things that you don't have to share data with me. I'm already understanding it by looking at you, right? We're not there yet. Building AI systems today, we're still capturing data the old-fashioned way, right? So we need to start thinking about new ways to capture data. The Terminator thing doesn't scare me at all. And the reason that it doesn't scare me, and especially you should, the mathematicians in the room, this is all differential equations, backpropagation. We know what this is. You, more than anyone, knows what's going on under the black box, inside the black box. The first mathematician that will tell me that is scared from differential equations or backpropagation coding, I haven't heard anyone. In fact, you probably love it and get excited. I really get excited about this stuff. Ernesto was telling me yesterday how when certain algorithms came around, such as differential equations or other things, people get super excited. Right? Today is transformers. Everyone's talking about transformers, right? We love this stuff. So are we afraid of these algorithms and models? No, we're not. Yeah, I mean, I should speak for myself. Maybe if you are afraid, I'd like to know that.
So let me just make two comments. This thing about understanding, like if you can write down the differential equation, you understand how it behaves. It's not entirely right, because we have systems like, for example, even the free body system, right? You can write down the equation, but it's a chaotic system. You don't really understand how it's going to behave. So it's just because you write down an equation doesn't mean that you understand what's going to happen. And the other thing, this is probably a very contrarian view. I would say that consciousness is not something. I mean, I don't know if maybe other people also feel the same. But I would say consciousness is not a purely human thing. I would say consciousness is more like a self-model. So I would say that all animals, or at least sufficiently developed. I mean, I'm less familiar with that, but definitely animals have self-models, right? Because they have to be able to navigate the world and separate the world from themselves so as to protect themselves. So they develop self-models, and I think that's basically consciousness. The difference between us and other animals is our ability to make up abstract concepts, and to manipulate them. Right. So that's the other. So yeah.
And even to the level, so this movie about Siberian Huskies, the first Siberian Husky, I forgot the name of the dog. It was so smart in all the things that the dog was doing, that it's difficult not to think that the dog, he was displaying such a level of abstraction in terms of how to do very dirty things in order to save some children. Actually, I don't remember all.
Also, I think.
Yeah, and it was so incredible in the level of depth, the depth that the dog was acting far more from just simply following the instruction, go here to there. It's far more. So I think that is.
And I know we have two more questions, but we're going to come back to this because it's not only animals. I'm going to show you some of the research that we're doing, which is very controversial, but it's going to show you how plants are also conscious. And the way that they act, not from obviously they don't have a nervous system, so it's not consciousness and intelligence as we know it. But I'm going to show you some of the research that we're doing that shows you how plants are aware. They have mental, not in the way that we do it, but understand their environments, mental models, and they take actions and plan. So yeah.
Just one question for you. I'm not very honest about AGI, you know, but because even we understand as human the abstract things, for example, in a equation, you know what is the vocabulary of that, right? The letters, but you don't know what's happening in that equation. So even you understanding the abstract things in that equation, I'm not talking about operations, something like that, but the abstract, like, you're seeing, you are writing the equation, you know what is happening there, well, with the letters, but you don't understand the abstract things more than just abstract. The abstract things has levels, right? It's not just like, this is an abstract, but it has levels. So for that, I'm not going to appreciate that. But if it happened that, what could be the real path that AI will follow? I mean, we have like advanced machine learning things, or they are going more that understanding the brain, the human brain, and will create something like a robot or something like that. Because being honest, I don't see where it could be the machine learning help to reach that activity.
You're absolutely right. You and I are on the same page. So I'm gonna, as we move on, I'll give you some ideas of what we're thinking. Yeah, but you're right. I think we're saying the same thing. The current state of how we're looking at this today, I don't think it's going to take us there. It's going to do amazing things. We're going to build great things like we're now, but is it going to take us to that level of AGI? Probably not. Yeah? Yeah, did you have a question?
I had a comment along the lines of most comments is that even assuming that we understand very, very well something, it can be pretty scary. For example, we understand quite well how H-bomb works.
Yes.
We understand very, very well how an H-bomb works. Nevertheless, I still find them pretty scary, and I still believe they should be banned. The mutually assured destruction game theory doctrine seems to be a little bit ill-conceived. Something could happen. You need to be lucky many, many, many times, and you just have to be unlucky once to be in trouble. Likewise, even though it can be extremely narrow intelligence, and even supposing that we get to an amazing level of understanding of its internal workings, nevertheless, it could be profoundly disruptive, even though, so I totally disagree with that.
Yeah, no, that's fair. But I would challenge that from the perspective that that's not necessarily a comment on AI. That's a comment on anything with it, right? Like the H-bomb, right? So I think that all technology that we create and we build has the potential to do really bad things, right? But in the context of AI, when we talk about the Terminator and we talk about things, robots coming to kill us, we really talk about that in the context of AI. And I personally don't think that AI is anything different than a technology that we're building to do potentially really good things, but we could do potentially really bad things, right?
But even if it is not evil, even if you just want, you remember this alignment problem where the AI just wants to make paper clips.
Yes.
Nothing evil about the AI, etc.
Yeah, so from the context of AI, I agree. I think we're now more conscious about, building, it's sort of an oversight of what gets done and are we doing it the right way. But really, we should be doing that with all technology that we build, not just AI, in my opinion, right?
I was just saying, like the lab I work in, and every day, well, all the labs at the medical school, I mean, they're genetically modifying anything you want.
Right, I mean,
Anything you want.
exactly. In the medical field,
And
it could be worse than
want to
anything.
continue with your lecture?
Yeah. So I'm gonna ask her first because she's.
So you have a-
And then we'll keep going. Yeah, last question for now.
Very quick. So I think Amari's lecture was like really like the example of things was like very, very striking to me. So I won't go into notes for once for the whole week. Right? We have formulas, and so we still don't know how the system behaves. So from that point of view, we know that AI can do a lot. We don't know exactly what it does, and that's just unsettling, right?
Yeah, I mean, I think you're right. You're absolutely right. We understand the underlying formulas and math behind it, but we train it with things that eventually can give us different results based on what data and what things we train it. And that's my experience, right?
Yeah, and then the other thing, like one of the reasons why I did not go to study psychology is because I don't even know what it means, a system that is as smart as a human.
Yeah.
Because we know that smart means you perform very well in some competition or some IQ test. In our world, it's known that artists and whatever don't perform well on these because they actually look for multi-field solutions and
Right. No, you're absolutely
so
right.
I don't even know what.
Well, I think in this concept, as smart as a human, that can be different things to different people. We might have an AI system that is intelligent. I mean, some people actually think that ChatGPT is intelligent. You know, some people think that other things are intelligent, right? And it depends on your context of what you believe intelligence is and what you. Yeah, but I mean, we don't even know. If I ask you to tell us, you know, what does intelligence truly means to you, the smartest person in the room can still have a hard time explaining what intelligence is. And I think that's the whole point. We still don't know what it means.
I don't even think that there's the smartest person in any room, right? Like I
Well, I mean,
think we
in the
don't agree
context
on
of
it.
what we're doing. In the context of what we're
But
doing.
even Schopenhauer, very early on, in the second volume of Will and Representation, has this chapter where he talks about animals and plants, and he's already very early on separates intelligence from consciousness.
Mhm.
He's, even for him, talking a long time ago, it was very clear that there could be intelligence without consciousness. Now, and then there is all these science fiction novels, you know, like
Right.
there is this civilization of intelligent beings that are not very conscious, and then the questions of whether a whole ant hill is conscious. Well, it's very clearly intelligent. Intelligence, yeah, it could be put in a narrow sense, like it performs well in certain tasks,
I have to remind you again that you have 15
Yeah, yeah.
minutes. Yes.
Yes.
and so on
Okay,
and so
so
forth.
but it's
Yeah, no,
fascinating.
you're absolutely true. You're absolutely right, Ernesto. So, okay, so I think we just spent like 20 minutes talking about the fact that we still can't define intelligence. So I think I made my point, right? So, okay, so AI algorithms, we've been working with these for decades. I mean, I started working, I'll show you the subset of the stuff I've been using for 25 years, right? So algorithms is not new. We know that, you know, the first algorithm, it's from minus 300 BC, the Euclidean algorithm, that's the first documented algorithm in his book called Elements. I think you probably know it. And that's the oldest algorithm that we know. So what happened from minus 300 BC until now? We hit a point in time, it was probably about 50, 60 years ago, when we figured out that we could literally take some of these equations, algorithms, and turn them into models like everything else, a step of instructions, but we could actually train them. And that's when the concept of, in the industry, the concept of AI came about. Because we could take algorithms and train them. And the moment that we train the algorithms with data, we knew that these systems could then start learning from data from, you know, by themselves, right? And this is just an example, a subset of all of the algorithms that we have been able to train since that first, you know, Euclidean algorithm, minus 200 BC, from minus 200 BC. This is just a subset of what we've been able to train in the last 50, 60 years. So if you remember when I was doing my PhD a long time ago, this area here didn't even exist. We spent all our time here. We typically separate them into supervised learning algorithms versus unsupervised learning algorithms. I spent most of my research 25 years ago working on convolutional neural networks, artificial neural networks, and supervised learning. We did a lot of work with the medical school, detecting cancer, all kinds of things. And then other areas started popping up. I just want to give you an idea of the context, the amount of work that we've done in the last 50 years to, in this space of trained AI algorithms. Right now, we're talking mainly in the industry, because it's the latest and greatest, we're talking about unsupervised learning and the reinforcement learning transformers. So everything we've discussed this week in the context of what we're building is only talking about one algorithm here. The transformer from 2017 is you all know, is the paper, the algorithm that allows us to do generative AI, that allows us to represent data via tokenization in different ways and do translations from one to the other. But we're all talking about this. This is the only space we seem to be concentrating on, which is, to me, is fascinating because we've done all this other stuff in the last 20 years.
Sorry, that's just a really funny name. Probably approximately correct learning. Is there?
Yes.
I don't mean to interrupt. I just what
Yeah.
I don't know.
Yeah, it's
another one is delta.
Yeah.
Like
It's
two
just a funny name.
Yeah.
Yeah.
Some do have funny names. Okay, so in the field, I want to share what we've done, some of the things that we've done in the field, working on, implementing AI, in what we call weaponizing in a good way to implement AI to give power to the people, right? So we have implemented these techniques, algorithms and models in hundreds and hundreds, over 450 plus implementations of these systems and models using these AI algorithms. We have used them in the last 10, 15 years ago with the Weather Center to predict hurricane tracks, to predict the weather. So we have tons and tons and tons of data. If you heard Ben's presentation, that's some of the models. We were working on early model generation for some of these models. So to predict hurricane tracks coming into the States, coming specifically to Florida and then the States. We use them to predict the likelihood of extinction by analyzing population response to environmental changes in the Everglades. So we have a lot of invasive species, like Brazilian pepper and other things taking over the Everglades. How is this expanding? Where is it going to show up next? So we did extensive amount of work predicting how this is moving across the Everglades. Conservation initiatives, detecting invasive species, also detecting, some of the things that are disappearing, like the Florida panthers. We have actually panthers in the state of Florida, and at one point in time, they're obviously very protected, but at one point they were in extinction mode. So we did a lot of work trying to track them, to see where we saw them, identify them from other species, and so on. Cyber. I worked in financial services for the last 20-some years. Extensive work in cyber, and this space alone is so fascinating. Because if you've worked at any global organization or large organization before, everyone needs a cyber organization to protect us from security issues. And traditionally, we've had, the cyber control rooms where we have lots of people in scenarios like these, looking at screens, looking for alerts and seeing when things are happening. Since we started introducing AI capabilities, AI agents to detect these cyber threats, in the near future, it's going to be my good guy cyber threats, cyber agents, watching out and keeping up with the bad cyber agents trying to attack us, and it's going to be cyber agents against cyber agents. And this whole, because it's happening in real time, it's happening faster. We can predict when things are going to happen before they actually happen. It's all about getting in front of it, predicting. So the entire space of cybersecurity is already changing, but in the next 5 years, it's going to be completely different, right? So it's super fascinating. And it's an area, I know that is close to your heart, right? From a cyber perspective. In financial services, it's being extensively used for fraud detection, personal financial advice, credit scoring, forecasting the market. We've done a lot of work on creating digital twins of the market, trying to figure out how certain geopolitical issues or other external agents are going to be affecting the market in a good or bad way. So the concept of digital twins, replicating real systems as a digital twin, and then introducing AI to be able to predict what's happening, it's booming. It's an area that's super exciting, right? And then for the last few years with my startup, one of the things that we've been concentrating on is on introducing AI to farmers. So we've been creating capabilities for farmers, smallholder farmers, to be able to predict nutritional issues, diseases in plants before they happen. Because right now, farmers go and walk the fields and they see that things are happening, but by the time the plants or crops are showing it is too late. So we're able to give them capabilities with AI to predict that they're about to happen 2, 3 days, 4 days before. The same concept of we know that the weather, with the weather, that a hurricane is coming 7 days before, we can now start predicting that crops are about to disappear. So by doing that, we can give tools to farmers to be able to get in front of the issues. Any questions about this? No? So the transformer model, which is the one that we've been talking about all week, is interesting, right? It's the latest model, the most visible model right now. And it's actually fascinating because it's allowing us to do something that we haven't been able to do with previous models. You know that page with all the AI algorithms that I showed you? The transformer is just one of the hundreds. It's fascinating because the notion of generative AI predicting, statistically giving you a next, word or stage is something that we've been doing for a long time in the context of GANs. So if you're familiar with GANs, when I was doing my PhD 25 years ago, we used to use GAN algorithms to create, we never had enough data. So we use GANs to create more data. We use GANs to enhance our data sets, create, shift or enlarge images or do deep transformations in data. But eventually, we have a better way to do it for data transformation, which is the notion of pre-trained generative AI, pre-trained transformers. So the generative pre-trained transformers, which is the transformers algorithm. So what's allowing us to do, which is super exciting, and we heard it at least 2 or 3 times this week, is that it doesn't only allow us to work with data. Hold on, I don't have it here. So GANs allow us to work with images and so forth, and video. Transformers allows us to work with any kind of data. And that's because it allows us to take data that we can represent it traditionally in a way that we have been representing data in a database. And it allows us to codify it, to tokenize it, and then to transform it from one to another. And this is fascinating. So some of the work that we're starting to pay attention to and work in the research lab is we are starting to work with bio data points, things like biomarkers, being able to capture from the biomarker perspective data, not necessarily images or data points, in a way that we can encode and then transform into another set. So this whole space of transformers is super fascinating. Okay? And that's why I think there's so much focus on it. However, we have an issue. Again, the difference between the value and the greatness of what we're working on and what's available versus the notion of, is it going to take us to AGI? And the answer is no. And we'll talk about this now, right? But of course, transformers are phenomenal, right? And we use them, we love them, we use them every day. We use Perplexity, ChatGPT, all the work that you presented, we're doing it. But they're not really scalable from the context of AGI, right? So if you think about it, the increasing complexity of LLMs or transformers in general makes them very expensive from an engineering perspective to train and to run. ChatGPT, for example, that was released in 2020, cost $5 million to train, 285,000 processors, 10,000 graphics cards, 800 petaflops of processing power. ChatGPT 4 from 2023 costs $100 million to train. And remember, when it's done training, you have to train it again because the data needs to be refreshed, right? And the expected cost of the future, which we believe is going to be ChatGPT 5, is $2.5 billion to train. How do you scale these? Seriously, like, what do we do with this, right? It's because of all the parameters, the complexity of the models, and the data, aspect of it.
They say that they're going to have a PhD level
Yeah, well, I mean, the joke, I mean, I don't know if, it might be serious, I'm not sure if it's a joke or if it's serious, but they're thinking about building these next to a power plant, right? So that they can have direct,
It's serious.
it's serious, okay,
Yes,
then,
of course.
of course. So, the costs are only computing resources, they don't include research and development data acquisition, other operational costs of running the interfaces, interference of these models, etc. So, this is just not scalable from an engineering perspective.
Yeah,
Yeah.
and that's why Wall Street investors have dumped these environmental startups and so on because they're moving their money to these
To mine
technologies
cores.
that they need money to take
To
care
inve-
of other
absolutely.
standards and so on.
Yeah, I mean, and this is actually something that we may not like in the long term. Do we want 3, 4 instances of massive statistical intelligence? I think if we want to replicate the notion of intelligence, we want to have a distributed, decentralized solution. That's just my opinion. I don't know what the answer is, but I'm not comfortable with this, right? On the other hand, put it in context, right? The human brain consumes 0.3 kilowatts hours per day for an average adult, which is the equivalent of 260 calories and 1088 kilojoules per day. Roughly, this is the same energy consumption and cost consumption of one light bulb.
So that's a very strong point actually against AGI, about reaching AGI
Absolutely.
in a
Absolutely.
shorter amount of time.
Absolutely. So from this perspective, we're not scalable the way that we're doing things today. Does that make sense? Yeah. So, okay, so I think I have two more slides. The characteristics of intelligence behavior. So we know that we have been trying to define intelligence by intelligence beings by, in a few ways. One, we believe that intelligence beings understand their physical space. They plan a sequence of actions. They are able to plan. You can understand your physical space. You're able to plan actions to reach a goal. You can reason, whatever that means, right? And we have to have some kind of working memory, because whatever I learned today, I gotta remember it tomorrow when I wake up, right? Or if I go to sleep, I gotta wake up and remember, So we have this working memory that's allowing us to plan in the future steps. And, what we tend to call this common sense. How do you know that I may or may not have common sense? Well, if I can say, I've seen this before, I've done this before, the notion of common sense is the notion of being able to remember things and being able to plan for the future, okay? And what's interesting is that we just look at that in the context of the brain, neural nets, or neurons, and then neural nets in computing. But there are other things that can do this as well, and they don't have a nervous system. So for example, plants, we have data, we have observed in plants that they have adaptability and flexibility. And we can talk about a lot of examples, but there's an example of a plant called the walking palm. We have it here in Florida, that it's half of the roots are underground, half of the roots are on top of the ground. And this plant literally walks itself to other locations when it doesn't have enough sun or enough nutritional issues. In fact, we have a neighbor that keeps telling us that his palm keeps coming over to his yard, and he has his palm and I'm like, come and get it. So we know that plants, in many ways, that we can go into details later, have the capability to adapt and the flexibility to adapt, okay? They have problem-solving skills, learning and memory. Plants, there are plants such as the mimosa plant here in Florida, in other places too, but here we have it. It's a little ground cover that when you go and touch it, it closes the leaves because it thinks that, to prevent any damage being done to the surface of the plant. And then the leaves eventually open up again. You go and touch it again and it closes the leaves. And then the third time you do it, or the fourth time, it won't close anymore. It won't close anymore. And that's because it somehow feel, or whatever the right word is for plants, it knows that there's no damage going to be done. So it just leaves them open. You do it a few times. Now, if you do it and then In 2 days you do it again, it closes it up. In 2-3 days you do it again, it'll close it up. But if you do it repeatedly,
So it's consciousness with Alzheimer.
it's conscious. There you go.
I mean, we assume that it does this because it learns that there is no damage, but could it be that it's because it just cannot afford the energy closing?
So if you do it, it could be, what we've seen is that it actually, so there are different frequencies of doing it, of closing, when you do it with different pressure points too. So there's a lot of research that goes beyond these. Pressure points, a kid's finger versus an adult finger, touching the mimosa. So I think I don't know, we don't know the math behind it. We don't know the model behind it. But we do know that at some point, when it detects that there's no longer a fear of destruction, or a fear, any kind of fear, somehow, however they translate fear, it stops closing, and you can come back the third or fourth times and do it harder, and it won't even close.
Can you
So-
move and then we'll
Yeah,
question?
And then there is another example that I mentioned in the next slide of plants talking about processing information. The brains of the plants are underground through the roots. And there's a notion of mycorrhizal network. It's a connection of fungus network that typically grows in good soil and connects plants to each other. And we have seen how when you have different plants in a yard, you can actually detect chemical signals and different types of signals going from one to the other through the air and through the mycorrhizal network. So in plants, we know that we have processing of information, we have situational aware, we have communication through chemical signals. If we have scenarios in plants, tomato plants, for example, that there is a moth that lays eggs, and the eggs grow into this caterpillar called the hookworm, which are really bad for the tomato plants because they eat all the leaves. We see that when a tomato plant starts getting eaten up by caterpillars, by the hookworms, it sends chemical signals to the other plants. Think about cybersecurity protection, right? Chemical signals to the other plants through the air saying danger. So these other neurotransmitters through the plants read the signals and immediately start emitting chemical reactions that prevents the caterpillars from eating the leaves. So we know that there is extensive communication going on. That we know it's happening, data points are there, we just don't know how they work, the formulas behind it, to be able to model these as a digital twin in a system.
That's very interesting, and probably people will have some reaction to that. But let's finish and then
Yeah.
we'll do the question.
So I think the models in nature, we know that they're there. We're capturing data. We're working on defining the stochastic models and deterministic models. From there, we are actually translating that to algorithms so that we can code it. So we are doing a lot of work in these. And my point to you as a takeaway is be aware that this is happening, because this is probably something that you're not thinking about beyond the notion of digital computing. Okay? So I give you some of these examples. This is the walking palm that's moving from my neighbor's yard to my yard. Mycorrhizal network, how plants communicate with each other. And we have many other scenarios. We're out of time, so I won't go into all the details of the research projects that we're working on. But we know that when we graft, for example, something on top of something that you're grafting, you take a little piece of a branch of a tree and you attach it to a root from another tree. RNA, mRNA flows from the root all the way up, and it changes the phenotypes of the top of the plant. So we have roses, regular rose bushes, that we're able to graft on top of other types of plants that make our rose bushes become vines and just take over. Right? And we still cannot, we know that's happening, data points, we can capture all kinds of data, but we still don't know how to put that into in a formulaic way. so that then we can feed that into our digital twins. Does that make sense? So we know that all kinds of things are happening in nature that we still don't understand, okay? And I just finished with this new data capture. We're working, supporting, advising a startup that is, for example, when you want to be diagnosed or you have a family member that needs to be diagnosed with some kind of mental condition, from low-level anxiety, something simple that most of us have, some anxiety, to something more severe, right? We know, for example, that today you have to go to the doctor, you have to be tested, you have to give some kind of either urine or blood sample so they can measure your neurotransmitters or whatever, your levels of your biomarkers. And then the doctor, when the result comes back, the doctor tells you you're low in GABA, high in serotonin, you have this or that, you gotta start taking this pill to feel better, right? That the whole process might be a month, right? So you take this pill for a while, and then you go back to the doctor, and the doctor might say, okay, keep taking the pill or stop taking your pill, right? So that's the legacy analog process. We are working with a startup that's actually able to, with the intensity of the cameras on our iPhones, the latest ones that are really, really good, high definition. We can look at the eye, and you can look at talk about knot theory, right? You can look at the shape of the iris, and you can see how sometimes when you have certain conditions, mental conditions, this knot shifts a little bit. And by measuring the geometry of this knot, they can start understanding certain mental conditions. Talk about how your research can be super impactful to people. And this can happen 10 times, not that you want to do it, but 10 times a day by looking at your phone. You can know what you have based on knot theory. So I think it's super important to figure out how you can actually take the research that you presented, that you're working on from a pure mathematical perspective, and figure out and understand and realize the impact that you can have in the industry. Does that make sense? So that's just an example. We'll skip all these other because of time, but just know that we're working on different ways to capture data. That's a different way to capture data. You don't have to go to the doctor. Eventually, to get a medication, you have to, obviously, and then you got to see an MD. But if you want to know if you have a high level of anxiety, you could potentially today look at your phone, an app, and with these knot theory calculations, you can potentially figure out what you have, which is fascinating. It's so fascinating. So we leave it at that. We're out of time, but these are all examples that we're working on in the industry, and they all map to your level of research on your mathematics. So what you're doing is really important. There's a lot more to do as it applies to going to AGI with chemical reactions, with other types of looking at data, right? And just be aware that that's happening. Okay? Any questions?
This might be the craziest one I've ever heard, all right? My brother told me that monarchs apparently have some kind of genetic memory.
Yes, they do.
Where like the monarch will be in this tree and
Yeah.
then it'll fly like, I mean like
we've done
miles or something.
We've done work with monarchs.
And then their offspring, like when they have babies or I don't know.
Yeah,
They'll come back to the same tree.
that's absolutely true. So we've done work with monarchs.
Monarchs have every year generation that is called the Methuselah generation, and it lasts like the time of 10 generations,
That's
just
right.
that alone, migrating back down to Mexico,
To Michoacan.
Michoacan, and they live all that time, just once per year,
That's right.
more than all the regular. It's like
Yeah.
one of us is suddenly lasting 1,000 years just to go back and to say,
No, it's true.
and to
And
start
it's
and
amazing.
It's super fascinating. So the lifespan of a monarch butterfly is typically 6 weeks, right? So that's how long they live. Other butterflies live from 3 to 6 weeks. The monarchs live about 6 weeks. But one at every third generation, because it's the seasons, right? So every third generation, when the third generation is born, that one butterfly lives 3 months. And that's because it starts, well, it gets to Michoacan, Mexico, which is a small area in the world, and it goes to the same trees in the same forest. And you can see that they're all latched onto these trees. The entire population of monarchs latch onto these trees in Mexico. And they go to sleep, and they sleep all winter. And that's why they have to live 3 months. They sleep all winter. But what's interesting is that the second generation that's starting to migrate to go to Michoacan, during the migration, butterflies, the migration process is still the lifespan of 6 weeks. So the butterfly the second generation that starts the migration today will die in 6 weeks. A new one's going to be born, which is going to continue down south, die in 6 weeks. The next one's going to be born, continue down south, and then die. The new one's born, and that one lives for 3 months. So this is absolutely true. They have, which we know that it's happening. The data points are there. We just don't know the formulas behind it, right? There is memory, not only memory, but environmental memory, but also generational memory. And imagine if we could truly put that into equations and understand that, what level of AI understanding can we have? You see what I mean?
Which is even worse because at the time it is, what is the word for that? Gusano. And it destroys itself totally to become a butterfly, and all the information is get lost and rearranged in such crazy ways. It's just so.
And I think that's this example of the monarchs. I can give you 10 other examples of situational, contextual, generational memory, right? That's happening in nature. So we leave it at least because we're out of time. Yeah.
Thank you very much.
Yeah, no
It was
problem.
very, very nice. If you have more questions.